start. So, hello everyone, my name is Luis Ramirez. Initially, let me just introduce myself. Based in Costa Rica, my major is in information systems engineering, and I have an MBA, or at least I'm working on an MBA in information technology administration. Uh, if you want to get in contact with me, these are my main contact methods by email, Luis Ramirez at northern.tech, and this is my Twitter account. Currently, I'm working for Northern Tech, the guys that develop Mender and CF Engine, as a customer success engineer. Uh, this was basically me, and what about you? This presentation is more focused on hardware developers or software developers, people that are related in some way with embedded Linux, and also RTOS or bare metal. Let's try to convey in some way, but let's see how this presentation develops itself. Please feel free to ask any question, and not totally sure how the platform works, but if I see any pop-up, let's try to cover that. First of all, let's talk a little bit about the OTA requirement checklist and talking in a more wider concept. Initially, we talk about we never can get a device in a brick state, always being able to boot it. So that's one of the reasons this presentation was created, one of the most critical parts. Then you need that your updates are atomic enough in order to avoid anything at the half. Then you should be able to do integrity verifications and even use signatures in order to avoid corruptions and make sure that the software that it's supposed to be delivered in the platform is as expected. And also, you need to make sure that the software that went from your system on the air, it's able to deliver exactly the same image till the end, and nothing else will be deployed to the platform. Let's say the right person will be able to deploy the right software to the right device in the end. So when we are talking about systems in general, the most popular flow, or one of the most popular flows, because there are different in this embedded environment, is the AB system update flow. This is the one that I am a little bit more expert on, where you have your image installed in a system, and then after some mechanisms, one of the parts of the device gets updated, one of the root file systems, and then the device is rebooted. If everything went as expected, then it will flag the update as successful. And if not, then there should be a mechanism to make possible a reboot. This is in its core basis how it will look like when we have the bootloader. That is the part that is really concerning this presentation. Then we have a redundant system, AB, where we have one system as an active one, and then we have the other root file system as an inactive. And in the end, we have a partition that usually is for persistent information. The problem, or not say the problem, but at least how it is designed, is that you have two components, or let's say two nature of components. In one side, you have persistent information, when in the other side, you have a transient one. What happens is that this transient in some way could be recovered, or you can play around with it. But if you messed with something that goes in the persistent side, sometimes it is not good at all. So in the end, as a summary, the problem with the persistency regarding embedded systems, or in general, is that once you break it, it stays broken. So basically, why shouldn't we have enough systems or enough mechanisms to ensure that these parts that are, let's say, a little bit more hard to roll back, we are able to fulfill this change, okay? So this is how people think nowadays how a bootloader works. We have the bootloader, it works, and then the OS comes magically. But the reality is this is how a real operating system, or let's say a boot process, a boot chain works. This is an example in ARM. So we have the boot ROM at first. This one is a little bit more, well, it's on hardware, definitely. To modify it is not an option. And it is pretty simple. It only allows you to do real basic operations. At this point, the concept of what is a root file system, or the concept of handling different storage devices, is not necessarily as simple. It has a pretty simple task in the end, that is to be able to trigger the next part. The next part is what we call an SPL, and the secondary program loader. It's called secondary, but you know that if we go to the userland, then this is really the first step in software. This part is quite small. Let's imagine probably like 16 kilobytes, depending on what architecture and what nature of device you are using right now. It has a little bit more complex access to the memory or the storage. Maybe it could understand what is a root file system, and in the end is the one that triggers the actual bootloader. In this case, everything that we are going to talk from this point is the actual bootloader. For the sake of this example in ARM, we are talking about U-boot. After this, then we have different processes that are not really relevant for this presentation. So if we already know these parts of the boot chain process, then we can imagine that the next step is to add some magic there, right? In this case, no, this is not what it should happen, because in the end, we are just adding another part, another segment to this process, and we are just overcomplicating the whole process without really earning anything. This is not a solution. So in the end, bootloaders are like a fire drill. You hope not having to have the need to update them. In the end, is not something that you really want to update because of the risks that are involved. But in the end, it's important to test, to have the mechanisms in place in order to make sure that if this extremely unusual situation happens, let's imagine you find any misbehavior on the field that was not captured when the device was developed, for example, then in that case, it will save your life. So in the end, what are the different strategies that we can use? Because we have the problem that everything that you can use here is really specific, really hardware specific. So there is no any strategy that it's one size fits all, because the bootloader location is not necessarily the same depending on the device. It is able to understand what is a file system. It is able to understand the flash partitions. It's able to work with signatures and key requirements, or even with configuration modifications. For example, can you modify some of the variables? At least in U-boot, you know it is possible. And how risky it could be, it will depend on what you are doing right now. So I would like to show you and share a couple of examples. In this case, we are checking a BeagleBone Black. In this case, U-boot resides in a FAT32 partition on the SD card. And in the end, it has a file called SPL that basically represents the SPL, and another file called U-boot that the real bootloader is located there. If we go to a Raspberry Pi, then it's quite interesting, because if you go to the folder /uboot, then you will realize that there is only a file called kernel8.image. But we are not talking about the kernel of the Linux here. This is really the name that Broadcom gives to the U-boot. So when we see this kernel8.image, we are talking about the U-boot for this particular device. We are talking about, if I can remember properly, this is a Raspberry Pi 364. Depending on the version and even the architecture, if we are using or we are talking about the system for 32 or 64 bits, the name of the file could change slightly. But in the end, these guys from Broadcom use that as a standard. Something that I didn't mention in the previous slide regarding BeagleBone is that the way that it works is that they use the name as the standard convention. So in the end, any file that has the proper name, it will be used as the bootloader. So in the end, what mitigation strategies you have, and in this case in hardware? Maybe you can consider to use a coprocessor or another device that in some way will act as a watchdog, and it will be able to catch if there is any problem on your actual update process. Let's imagine that the bootloader was changed, it didn't work as expected, so you can use this other, let's say, coprocessor to restore in some way the bootloader. That's one of the alternatives. And in the end, it will depend of the vendor of your SoC. This is a quite a simple example of how it works. This is, for example, in the case of BeagleBone, and they have something interesting that a lot of providers has as well. That is, it has a strategy to check in different devices. For example, it checks the SD card. Okay, the SD card is bootable. It is not. Okay, let's check the internal memory. It is not bootable. So you can, for example, create this list of different points where to check and use them even for to restore if something gets broken. Something really important is to make the vendor handle this part for you if that's possible. And in some ways, if you go with UEFI devices, then in x86, then to modify UEFI is not that a big deal compared to other, let's say, providers or any other methods. If there are vendors, for example, NVIDIA, that they have different mechanisms in order to perform updates on their bootloaders as well. And you can check on their documentation what are the best practices. So always trust your vendors. And if you are an integrator, don't invent the wheel. And sometimes the vendor itself will provide you with that. This is a simple example on how the NVIDIA Tegra boot process works and how it could be updated. In this case, we are, if we check some of the providers of OTA in the market, in this case, Mender, that is the one for I'm working, there are currently available a layer for the Yocto project that you can use in order to modify a little bit the process. If you deep dive in the layer, you can find files like this, and you can modify the content in order to add your customizations. If we are talking again about the Yocto project approach. Also, in their one of the latest versions, I'm not really sure if it's still the latest or not, but in Jetpack 4.6, in L4T, that's the system they include based on Ubuntu 18, they provide even redundancy regarding the bootloader. So they provide their own application that basically wraps the different components of the software, let's say the bootloader, the root file system itself, and this tool easy your life in terms of updating these complex parts. In the end, or as a conclusion, it's important to plan the bootloader updates, and hopefully you will never need it, just as the example of the fire drill. It's a good practice to use flexible software for performing OTA. In my case, I am a user of Mender, but there are several other providers on the internet. Then a second option is to use a hardware approach. It could be a little bit more costly, but on the other side, it could be more robust. It will depend. But on the other side, it will require high effort and probably a software as well. And finally, the plan C, but it could be even your plan A, is to look for support from the vendor, because in the end, they already know the best practices that you can use. And the only problem with this is, depending on the platform, probably it could or not be available. So I hope you like the presentation. These are some mechanisms that you can get in contact with me or any of my peers. And yeah, that's all. Thank you for your attention.